Today's video is going to be focusing on Lewis structures, which is a visual way for us to illustrate how elements are going to either exchange or share their electrons to form these molecular shapes, which we explored in our last lab. So we're going to start off with just some basic terminology and then go into drawing out Lewis symbols, which help give us these individual pieces that combine together to form the overall Lewis structure. So in terms of the electrons we're going to focus on, we really only care about that outermost energy level, what we call the valence electron. So these are the electrons located in the outermost principal energy level. And the maximum number of valence electrons, again, for any element is 8. We can't exceed 8, which is what we refer to as the octet rule. Okay? So when we talk about a particular element, like, for example, sodium, its location on the periodic table can help us visualize its electron arrangement. Right? So remember that the row that it's located in tells us the energy level that that last outermost electron is located. And then the group that the element is located in is how many electrons are in that particular energy level. So if we look at sodium here, it's in the first group and the third period. So our orbital arrangement and electron configuration for sodium would have us fill in 1s2, 2s2, 2p6, 3s1, and since the highest energy level that electrons are located in is that third energy level, sodium has only one valence electron. Okay, and so that pattern does kind of repeat itself as we compare every other element on the periodic table. All right, if we were to jump over to chlorine, which is still in that third period, but now it's in this seventh column or seventh group, chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5, and again, the highest energy level that electrons are added in is the third, and in total, we have 7 valence electrons. Okay, so what I would have you add here is that your group number is your valence electron number. Okay, so if the element's in group 2, it's got 2 valence electrons. Group 5, 5 valence electrons. Now, when it comes to actually drawing out the symbol, this is one of the necessary initial steps to help us figure out this overall structural shape. So the symbol is actually pretty simple. You start with the actual element symbol. So sodium is element Na. And then we're going to draw around this, kind of like adding in prongs of a puzzle piece. So we want to visualize the element existing within this box. And we start with one element at the top. And we're going to add in 1 electron per side. Because remember, we've got orbitals that can only hold a maximum of 2 electrons. And then we're going to, as we add the number of valence electrons surrounding each side of the box. So sodium only has 1 valence electron, so it only has 1 electron when we start at the top part right there. So we can kind of visualize that as like one prong to a puzzle piece that's looking to fit its way into another element's location. Okay, if we repeat that example with our chlorine, we've got the box around chlorine again, but this time we've got 7 valence electrons that we need to add in, and we're going to start by putting 1 electron per box. And if you remember that Bus rule or Hund's rule, the electrons don't like to exist in the same orbital unless they have to fill in that entire energy level. So as we add these 7 electrons in surrounding chlorine, we're going to put the second one on one side of the box, the third one on a third side, the fourth one on that fourth side, and we still have to add in the 3 remaining valence electrons. So that's when we go back in and put in one there, and then one there. So we've got 7 electrons surrounding chlorine. And again, this also gives us an idea of why we always have a maximum of 8 valence electrons. The actual space and the outermost energy level for every element can only hold 4 orbitals, which each have a space for 2 electrons, so a maximum of 8 total electrons. And then in terms of an actual puzzle piece, we've got this kind of a thing going on here. And we start to see where we've got an opening for 1 electron and another element that has 1 electron to give. And that helps us to visualize where these compounds and these formulas are actually going to start to form and take shape. Okay? So if we finish out our last example, we've got carbon, which on our periodic table is right here under group 4. So that means since it's in the 4th group, it's going to have 4 valence electrons. And as we get ready to draw the Lewis symbol for carbon, again, we're going to draw the element symbol. We can start visualizing it as existing within this box. And then we're going to put 1 electron per side until we've reached the maximum number of valence electrons for that element. And so this would be carbon's Lewis symbol. And as a puzzle piece, it has some pretty intricate arrangements where it's got 1 electron per side and openings for 4 additional electrons to be added in, or for those 4 electrons to be donated. Okay, so drawing out a Lewis symbol is our kind of initial step, like I said before, to get all of the puzzle pieces that are eventually going to fit together to form these overall compounds. Okay. So our last unit helped us to understand that we've got 2 different types of compounds that can exist. We've got ionic compounds or ionic bonds, and covalent compounds are what we refer to as molecular bonds. Covalent is just another word for the molecular compounds that exist between 2 nonmetals. Okay? So remember that when we talk about ionic compounds, metals like to give electrons and the nonmetals like to take electrons. So anytime a metal is involved, the metal is looking to actively give up all of its valence electrons, and the nonmetal is looking to actively take all of those valence electrons. We refer to it as a give and a take. Okay? When we get to covalent compounds, which are made up of only nonmetals, they can't all just take electrons to fill their octet. This is where we were talking about there's like a different form of bonding that's occurring. And so the nonmetals actually share all of their valence electrons so that if they overlap, they could each have that octet rule. So all nonmetals are looking to overlap their orbitals and have their electrons essentially count twice so that each nonmetal can have 8. Okay. So this is where we get to this idea of drawing what's called a Lewis dot structure, which is a shorthand visual of valence electrons using the element symbol and then dots to represent the electrons between those elements. Okay. So if we're drawing the Lewis structure, which is now either the formation of an ionic compound between this metal and this nonmetal, or the formation of this molecular compound between carbon and chlorine as 2 nonmetals, we have to use the Lewis symbols that we drew earlier as our starting point. Okay, so if we quickly sketch down here, we've got sodium with 1 electron, 1 valence electron up top, and then we've got chlorine. And again, if we get in the habit of drawing it in this clockwise notation, we start to see how there's one side here that needs a second electron, and sodium has that 1 extra electron to donate. And so what we want to visualize is that this electron is going to be donated by the metal and then accepted by the nonmetal. And the way that we draw this, whenever there is two electrons that are being essentially shared, I shouldn't say shared, being donated and received within this ionic compound, we're going to draw that as one line, as a bond between that metal and the nonmetal, but we can't exclude all of those other electrons that chlorine had originally. So although it doesn't look like it, sodium actually is following its octet rule because it got rid of its one valence electron, and it's now going back to this original core set of electrons, which adds up to 8. Okay, so this would be the correct Lewis structure for an ionic compound between sodium and chlorine. Right? We also refer to, anytime we see the side of an element where two electrons are already located, we refer to that as a shared pair, or a bonded pair, as a shared pair of electrons. There's no room for another electron, and they also don't want to donate any of those electrons. So those usually refer to sides that aren't going to form any additional bonds. Okay? Now, when we get to this last example, carbon tetrachloride, we've got one carbon, but now we've got 4 chlorines that are trying to bond onto that one carbon. And so we get this symbol here for carbon, which again we drew up above, but we have this idea that there's now 4 locations on all 4 sides of that carbon atom that are trying to bond. And we have to get in the habit of making sure that our Lewis structure incorporates all of the elements that are as a part of the formula. So we're trying to make this compound between one carbon atom and then 4 chlorine atoms. Right? And then another thing that we can kind of get in the habit of doing is, although this element here, like for sodium, was drawn at the top, and then over here it just kind of appears on the right side, these electrons don't like force themselves to stick to the northern part of the element or the southern part of the element. They can be rotated, and then this like could form a bond that goes off to the right. This could, like this chlorine bond doesn't have to be overlapped like on the right side. This one could be drawn where it's on the bottom. If I like quickly erase this, what we could do is we could have had 2 pairs and then had one on the bottom right there so that it can bond downwards and then connect with that top electron. They don't always have to have like one side where the same electron is by itself, because you could have started your count on like one side and then rotated around. Okay, so hopefully that clears up and makes a little bit of sense there. Right, but we do understand that if we've got a molecular compound, these electrons here are trying to share and connect a multitude of different ways, all in an effort, again, to reach this octet rule. Every element is trying to have 8 electrons. So when we draw this, although this looks kind of messy, it gives us a better understanding to know that carbon is going to try and form 4 individual bonds, and chlorine, because it has these 3 pairs of electrons already grouped together, each chlorine is really only wanting to form only one bond. So when we draw this cleaned up final structure, we're going to draw the carbon in the center and have 4 what we refer to as single bonds coming off of that carbon. And then again, we have to go back because the original Lewis symbol for chlorine has these 3 pairs of electrons. We still have to have that in our final answer. So this would be the correct Lewis structure for carbon tetrachloride. Okay? So there's a couple of things that we want to take into account when we draw out our final answer. One of them is the total valence electron number. Okay, so here we've got 1 sodium, which again is in group 1. So that means that it has only 1 valence electron. So sodium brought 1 valence electron. And then we've got 1 chlorine, which again is right here in group 7. And so it brought, let me line my camera up here. It brought 7 valence electrons, so we had a total of 8. So in our final Lewis structure, we can only have 8 total electrons illustrated in our final answer. And remembering that this line is a pair of electrons, we've got 1, 2, think about them as like the segments at the start and end of the line. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Right? The other thing that we know to look for as a correct ionic Lewis structure is that the metals have given up all their electrons to the chlorine or to the nonmetal, and that the chlorine, that nonmetal atom, has a full octet. Okay. When we do our total electron count for carbon tetrachloride, we've got 1 carbon, which is in group 4. Okay, so carbon brought 4 valence electrons to the Lewis structure. And we've got 4 chlorines, which each have 7. So there's a total of 28 electrons from all of the chlorines, which means we should have a total of 32 valence electrons in our final Lewis structure. And so as we go back and count within this circled area, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, so that's one critical step, that our final Lewis structure has the correct number of valence electrons. And then the last thing is to make sure that every element is satisfying this octet rule. Chlorine has 2, 4, 6, 8 electrons surrounding it, and every other chlorine does as well. And carbon has 8 electrons surrounding it as well.